Hi everyone. Today we'll be presenting our project on hybrid graph reasoning for residential floor plan generation. I'm Tor,
I'm Jonathan.
and James and Yufei are also on our team.
Our goal is to generate realistic residential floor plans from graph structured inputs. The input is a graph where nodes represent rooms and edges represent their connections, and the output is a set of spatial masks. This problem is challenging because geometrically, rooms must have realistic shapes and sizes, and topologically, they must maintain correct adjacencies. More importantly, ensuring a consistent overall structure across the entire layout is much harder. The problem is important for applications like architectural design and real estate visualization. However, prior work mainly relies on local message passing, which makes it difficult to capture long-range dependencies. Prior work, like HouseGAN and HouseGAN++, uses graph-based GANs for this task. However, these methods rely on equal weight message passing, meaning they treat all neighbors' room equally. This creates two key gaps. They ignore relative importance between rooms, and they fail to capture long-range dependencies like bedroom to bathroom relationships. Our work addresses this by introducing attention-based architectures. Our work is a re-implementation and extension of the HouseGAN++ framework applied to the REST-plan dataset, which contains geometric layouts of floor plans and structural relationships between rooms. Each floor plan is originally represented as a vector layout, and first we construct a graph that captures adjacency and connectivity. This serves as the input to our model, and then secondly, we extract individual room masks, which serves as supervision during training. Due to the baseline's limitations, we then explore three extensions. First, Graph GPS adds global transformer attention on top of local message passing. The goal is to allow each room to attend to all other rooms and better capture long-range dependencies. However, we found that global attention alone is not always sufficient. So secondly, the hybrid model combines global reasoning with local spatial features. This gave our best qualitative results. Lastly, the pure transformer treats rooms as tokens, eliminates spatial inductive bias, and relies solely on token-level attention to capture a relationship between rooms. This slide shows the full architecture comparison, and the key idea is that the baseline uses local message passing, Graph GPS adds global attention, and the hybrid combines both, and the transformer emphasizes on attention. In addition, we use a curriculum training strategy. We first trained the model in a supervised setting to learn basic room layouts, and then introduced adversarial training while adding front doors. Then we incorporated full adversarial training while generating interior doors. This stabilizes training since GANs are very unstable early on. For evaluation, we use IOU to measure mask overlap, but since it does not fully capture layout quality, we also track failure cases such as empty or oversized predictions. And we reported FID and GED from the original report to measure how well the generated layout matches the input graph structure.
For Graph GPS, we see that fixed rooms are generated accurately. However, non-fixed rooms fail. They appear as blobs rather than structured shapes. This suggests that global attention alone is not enough to capture spatial structure. The hybrid model improves spatial structure. Rooms become more rectilinear and realistic, but we see a new issue. Door placement collapses with near zero IOU, so adding local structure helps, but introduces new challenges. In the final hybrid model, fixed rooms and front doors are nearly perfect, but non-fixed rooms are still inconsistent, and interior doors are essentially not learned, so the model still struggles with full layout completion. Here we see some results from the inference. For the pure transformer, fixed rooms collapse into uniform shapes. Non-fixed rooms are completely empty. This shows that without spatial inductive bias, the model still fails entirely. Quantitatively, the hybrid model achieves the best FID. However, this is insufficient because FID only evaluates valid samples. Models with fewer valid outputs can appear artificially better, so standard metrics don't fully capture the layout quality. Our original hypothesis was that attention could improve layout quality by capturing long-range room dependencies, but in reality, performance did not improve. We identified three main reasons. First, compressed representations lose spatial information. Second, the discriminators expected baseline models distribution cause unstable gradients. And third, the model is too large for the dataset size. Another key issue we found during error analysis was that the data had room categories that often are very small fragmented regions. After rasterization, these often become thin sliver artifacts that visually resemble doors, which confuses the model and pollutes the training signal. To address this, we added simple filtering during preprocessing, removing regions, and bounding box size. In summary, we found that WGAN GP training is unstable and on sparse layout data, and that combining local and global reasoning through the hybrid model works best. We also saw that dataset quality plays a significant role, and preprocessing artifacts can negatively impact training. Overall, generating coherent layouts remains a challenging problem, especially when moving beyond fixed room structures. For future work, we plan to complete transformer training, improve dataset preprocessing, explore diffusion-based approaches, and incorporate higher resolution with better connectivity constraints.
Thank you.